All right. So last class period, or last unit, we were talking about gases and how do gases change. We change like the pressure, the temperature, or the volume of the gas, and then what kind of calculations you could do with that. So today we're going to kind of change up what we're talking about. Unit 11 is all about solutions. So solutions just things mostly dealing with water, but it can be things other than water as well. So like what are these things when they're mixed up? What are some calculations we could do with that? What are some things we can observe? And what's the vocabulary that we need to know? So for this particular lesson, we want to define exactly what a solution is. We want to kind of briefly explain what polarity is and its role in water's properties as a solvent. We want to define the three different levels of solution saturation. So like what is saturation and what are the three levels there? And then probably by next class period, we'll start interpreting these things called solubility curves, and we'll describe some factors that may affect what's called the rate of dissolution. All right, exciting.
Solute.
So solute,
No,
it's not solute. All right, so what is a solution? Well, quite simply, it is a solute dissolved in a solvent. Okay, so to dissolve something, y'all should recall, hopefully from your day-to-day lives, if you like, put like a sprinkle of salt or sugar in some water and you stir it around, what happens? It just disappears. Oh my goodness. But it's like evenly mixed into the water and that dissolves. So the solute is the thing that gets dissolved. Like the sugar that you're trying to dissolve in water. Example, sugar. And then the solvent is the thing that does the dissolving, the thing that gets dissolved into. So, for example, the water that we dissolve things into. Sometimes it gets a little bit confusing, like, oh, what's dissolving into what? Like, is it like a half and half kind of situation? In any sort of situation where it's a little confusing, basically the solvent is always the thing that makes up the most of the solution. So, of like your little mixture there, as long as you say the solvent is the thing that makes the most of it, then you correctly labeled what's the solvent. Everything else inside the solvent is called the solute. So if you mix cream into your coffee, what's the solute and what's the solvent? The solute should be the cream, and the solvent should be the coffee, exactly. Okay, so once the solute is evenly dissolved, what do I call the new coffee? Good. Now, you can call it a solution, or and this is blast from the past a little bit. Oh, this thing keeps falling off my head. I'm putting it around my neck. All right, a solution or a homogeneous mixture. Um, so remember, we had heterogeneous mixtures, things like, sand, Rocky Road ice cream, things like that. And homogeneous mixture where things are very evenly distributed, completely the same throughout, like cream, milk, sugar water, salt water, things like that. Okay, so what are some characteristics of solutions other than like they seem pretty mixed and evenly, homogeneous? Well, our solute doesn't settle. And I don't mean it's really hard to like date your solute. I mean like what happens at the bottom of your beaker, like or your cup or something. Like does sugar fall out of water over time? No, it's not going to settle to the bottom of the glass like that. If you go to the grocery store and you're looking at like a can of Coca-Cola, or like a clear bottle of Coca-Cola, you don't see all the Coca-Cola fall to the bottom really. But you might go to the orange juice aisle and see like all the orange juice kind of settle to the bottom. So the orange juice would not be a solution, but then the Coca-Cola would be. Your solutions can't be separated. Let me elaborate on that. Can't be separated via filtration or filtering. So for example, if I have like a coffee filter and I like run some salt water through it, some sugar water through it, some coffee through it, it's not going to completely separate anything out of that. It's going to be the exact same liquid before and after I run it through a coffee filter. How can I separate a solution? I could just let it evaporate, or I can boil it off, one of those two. Exactly. And then also we might have different properties, like chemical or physical properties. So, if I'm making some salt water, my salt crystals are going to look different than the stuff I'm mixing it to. The water is going to be different than like the saltwater solution. For example, now the water is harder to freeze, it's harder to boil. Um, the water can now conduct electricity really well if I dissolve salt into it. And also, the salt crystals are no longer solid salt crystals, they're dissolved into the solution. So we change the properties of the things that we turn into a solution. Okay, let's talk about states of matter of our solutions. So normally, like if we have a solution, it could be like a solid, liquid, or a gas, actually. Solutions are considered to be in one state of matter. Oh, one state of matter, doubling words there. But it can be made up of any combinations of states of matter for their solute and solvents. So my solute can be a solid, liquid, or a gas. Or sorry, my solution can be a solid, liquid, or a gas. But it can be formed of things of different solid states of matter. Like my solute could be a liquid, gas, or solid. My solvent can be a liquid, gas, or solid. So for example, a liquid and a liquid, we just mentioned one. We had cream and coffee. We can combine those and form a solution. And those two are liquids that come together and form a solution. Other examples you might think about are like a cup of vinegar from the store. It's not just vinegar, it's vinegar and water, and it forms a solution. Huh? Milk and chocolate syrup, making some chocolate milk, that's another good solution. Gas in a liquid, so dissolving gas in a liquid, one of the most common examples from your life is carbon dioxide in water. That gives you carbonation. Like if you're ever like, oh, some carbonated drink, I really like carbonated water, or I hate carbonated water, I hate the feeling it gets me. That is because there's carbon dioxide dissolved in there. Another thing there is like you might hear like, oh, how do fish breathe underwater? Well, they have gills, but what are they breathing? They're still breathing oxygen. That's because there's oxygen dissolved in the water. And if you have a fish tank and you don't bubble it correctly, then there's no way that there's more oxygen that will dissolve in the water and the fish will just die. They'll suffocate. Yeah. All right, a gas and a gas. Yes? The word next to water, I put carbonation. Carbonation. Something's carbonated or not. Now, a gas can also be dissolved in a gas. If gases mix together, we also call it a solution because it's a homogeneous mixture. So any sort of air that we breathe, that is a gas dissolved in a gas. So the atmosphere is filled up with nitrogen gas, and it's like 70% of our air. But then dissolved in that nitrogen gas are things like oxygen, argon, carbon dioxide, things like that. So we're always breathing in a solution of air. Now, solid and a liquid, that's a pretty common example. For example, salt water or sugar water. So like salt and water might form like seawater, for instance. That salt will easily dissolve in the water and then form a solution. A solid and a solid. Can solids dissolve in each other? Oh, kind of weird. There's actually one type of solid that can dissolve, and that's when we're dealing with metal alloys. So an alloy is when you have a metal with another metal. So some examples of alloys are things like any sort of aluminum in your phones. Normally it's like an alloy strengthened with like some bits of chromium, things like that. If you ever use stainless steel in your kitchen, that's actually an alloy between iron and like carbon and chromium, things like that. And then other two common alloys you might hear about like in your history textbooks are just having these things in your house. Anything made of brass. Brass is commonly a solution between copper and zinc. So like maybe some brass doorknobs or something like that. And anything like bronze. You might have heard like, oh, the Romans used bronze weapons. Bronze is usually made from copper and tin. And you melt these down together and they form a solid solution, evenly mixed and distributed. Okay, let's talk about solubility. So what is solubility? Well, it just refers to the solute's ability to be dissolved by the solvent. Like, can something dissolve or not? That's the solubility that we're talking about, solubility. So a substance is considered soluble if it's able to be dissolved in a given solvent. So for example, salt is soluble in water. Um, Sugar is soluble in water. But a substance is said to be insoluble if it stays in its original state in a solvent or it does not dissolve. So I find some random pebble outside. I put it in a glass of water. It doesn't even change. It's still the same pebble. Okay, so that random pebble is insoluble in water. My plastic cup doesn't get dissolved by my water. It's insoluble by water. One more vocab term that you might hear from time to time. It's not as common, but it's still useful to know. What if a liquid can dissolve in another liquid? That is called being miscible. miscible, miscible. And if a liquid cannot dissolve in another liquid, that is called immiscible. Immiscible. Um, let's see, liquids that dissolve in other liquids. Um, any sort of like essential oils and stuff, normally they're dissolved in like other oil. Like for example, peppermint oil, it might be like some like actual peppermint oil dissolved in like maybe some argan oil, some olive oil, something else that kind of like dilutes it a little bit. Um, Liquids that do not dissolve in each other that are immiscible, you can just think of things like oil and water, like salad dressing. They don't really mix. They kind of form separate layers over time. So let's explain like why that happens. Like why don't oil and water dissolve each other? Well, this has to do with this concept called polarity. So if something is polar, that means having oppositely charged ends. So if you look at the molecule itself, there's going to be kind of a positive end and a kind of negatively charged end. So when I say positive and negative, that kind of goes back to electrons and protons. Like more protons means something's positive, and electrons means things are negative. And we talked about ions, where okay, cations are positively charged, anions are negatively charged, and they're like kind of like magnets, like two different sides of the magnets. And we also said that there's such things as ionic compounds, which are formed from the attraction between these positively charged ions and negatively charged ions. So this concept's kind of related to that. So we can kind of separate our substances into things called polar substances and nonpolar substances. So polar substances include things like ionic compounds, acids, polar covalent compounds. There's going to be some more examples I'll mention in a bit. And nonpolar substances include nonpolar covalent molecules and diatomic molecules, or anything that's super like symmetric. So water is known as a polar substance, and that means it has opposite ends, a positive end and a negative end. And just to kind of briefly explain, why does water have a positive end and a negative end? Well, a water molecule kind of looks like this. Like you might see it drawn like this, where it has like these shared pairs of electrons, kind of going back here, where we had our Lewis dot structures. A water molecule look kind of like that. And lots of times a water molecule might even be like displayed like this, just like three circles, where the big circle is the oxygen, and then the little circles are hydrogens. But let's talk about what's going on here. So normally we have several electrons, like these little dots all around our covalent compound. But the thing is, this oxygen, it's extremely electronegative. It really likes electrons. It will pull electrons towards it. So if you look at this picture here, notice that the shared electrons between the oxygen and the hydrogen, they start pulling a little bit closer to the oxygen, just a bit closer. And if electrons are a little bit closer to one end of our molecule, that means there's more negative stuff on that side of the molecule, which means that this side of the molecule is going to be partially negative. It will have a partial negative charge. And the side of the molecule that we took away the electrons from, now it has a lack of electrons. Because you have a lack of something negative, now you are partially positive. So the side of the water molecule with hydrogen on it is partially positive. So every single water molecule has like a partially positive side, a partially negative side, making it polar, making them like little mini magnets. So if you put a bunch of water molecules together, all of a sudden, like, we have water molecules attracting like the positive side to the negative side, the positive side to the negative side. If you put anything else that's polar in here, like, I don't know, let's call it a random plus minus molecule, then the water molecules will kind of like start surrounding that as well, and they will let that dissolve into that substance. Okay, lots of random pictures. So polar substances are able to dissolve polar substances, and we can kind of summarize this rule as this rule in chemistry called like dissolves like. So things that are similar will dissolve each other. The other things are similar. So, for example, polar substances dissolve other polar substances. Nonpolar substances dissolve other nonpolar substances. And then we can also say that polar substances will not dissolve nonpolar substances, and the other way around. Nonpolar substances will not dissolve polar substances. Um, so, what are some examples of this? Well, we did say some things are polar and nonpolar before, but some things you could think of as polar are things like salt, sugar, um, water. Water is the universal solvent. It's a so-called universal solvent because it is very polar, likes to dissolve a lot of things. All that mixture of grime on your sweat, all that stuff is polar, so it can be dissolved with water very easily. Non-polar things include stuff like plastics, oils. That's about it, plastics and oils. So they will not be dissolved by water. They don't like dissolving in water, but they'll dissolve other oils, other things kind of based on that. For example, if I were ever to put like stylish nail polish on, I can't really wash it off with water, but maybe I can use like nail polish remover. And nail polish remover will kind of dissolve that a little bit more because nail polish remover is more nonpolar than water is. And nail polish is very nonpolar. So why do you think oil and water don't mix? Because oil is nonpolar and water is polar. And what about soap? Why does soap kind of is able to wash off grease? It kind of dissolves grease, but it also gets dissolved in water somehow. So soap is polar and is nonpolar. So it's able to dissolve grease in water. Let's kind of complete this here. So, and if I were to draw out, I'm not going to do this, but like if you were to draw out molecules of a soap molecule, like the active ingredient, the soap itself, the suds, the detergent, they might call it. One side is kind of polar and the other side is more non-polar. So both sides kind of like group these oils and waters together. That lets you like wash things that you wouldn't be able to otherwise. Questions so far? All right, let's skip this next section and not return to it. The dissolving section, that's a little esoteric. I think the word esoteric is esoteric. It's ironic. Okay, something we do need to know how to do is kind of interpret this solubility rules chart. So we see this chart here, and we're going to kind of decipher it and kind of come up with some examples from it. But you will see this on some future tests as well. And the whole point of this chart is that some substances, some ionic compounds, so things with a plus charge and a minus charge, dissolve in water, and some don't. We did say that ionic things tend to dissolve in water, but some of them just do not. You will put them in water and they stay as a solid. They don't do anything. So you can use rules to predict what will dissolve in water. Now, in general, there are some rules that will tell us that something's always going to dissolve in water. If you have any ionic compound that contains an alkali metal ion, basically group 1 on your periodic table, anything like Na plus, K plus, Li plus, then it will be soluble. If you have any compound that contains ammonium ions or NH4 plus, that will be soluble. Anything with a nitrate ion or NO3 minus, that will always be soluble. But those are just things that are easy to remember, but you will have a chart that kind of like tells you all these things as well. It just takes a while to read sometimes. So on the very first half of our chart, we have things that are supposed to always be able to dissolve, with some exceptions over here. And then on the bottom side here, we have things that shouldn't really be able to dissolve, with some exceptions a lot more exceptions over here. So we can kind of come up with some examples of things that could be soluble and things that aren't soluble. So for example, three soluble compounds using the chart rules. I could look at this first part of the chart and think to myself, okay, I don't know, I'll pick like CN, cyanide. Maybe just some random thing with cyanide. Calcium 2 plus with cyanide would be Ca, CN2. Okay, that's supposed to be soluble because cyanide's always soluble. Oh, what about Br minus? It says Br minus is mostly soluble most of the time. So let's come up with something. Maybe SR Br2. Okay, that compound probably soluble. Strontium bromide. I don't know. SO42 minus sulfate. Okay, so with some exceptions, this should always be soluble. So maybe like aluminum sulfate, so AlSO4, and then it should be Al2SO43. Okay, that should be soluble. I don't know. I'm just coming up with some random things. No hard and fast rules for this question. Just giving you some examples. Things that are insoluble using the chart rules. Okay, let's look at things that are insoluble. Maybe something with carbonate, the CO3 2 minus. I don't know. Calcium carbonate, CO3, CaCO3. Okay, that should be insoluble. It will not dissolve in water. Something else. What about something with OH minus, hydroxide? Well, it says that maybe something like, let's say gold hydroxide, AuOH. I don't think that will dissolve in water. And then just making something else up, maybe something with this phosphate, PO4 3 minus, maybe like silver phosphate, Ag3PO4. Just some examples here of things that will not dissolve in water. So hopefully you'll be able to kind of read that chart. Just kind of go, like if you're looking for something that's soluble, look at the soluble section. Make sure you check the exceptions. If you're looking for something that's insoluble, check the insoluble section below and look for some exceptions of that, just to make sure it's insoluble or not. Okay, let's talk about saturation really quick. Do you think you could dissolve a whole bag of sugar in a cup of water? No. Like that's supposed to be for like 3 cakes, right? So like it's too much sugar. Why or why not? We'll just say no, because there's a limit, right? There's a limit, and that limit is called the saturation limit. The saturation limit says, how much you can dissolve. Like how much solute can you dissolve in solvent? And it really depends on like what materials you're using. Like what's your solute, what's your solvent? Most of the times we're going to look at saturation limits for water. Now, can saturation limits change? Yes. For example, you can change the temperature and that will change your saturation limit. So let's talk about this for a sec. Let's say I'm obsessed with sweet tea. It's actually been a while since I had sweet tea. I don't know, too much sugar is bad for you, but sweet teas taste pretty good. Now let's say I forgot to make it sweet tea. It's just tea, unsweet tea. And I add ice to it, and I'm like, oh darn, I need to add all my sugar still. So I add sugar to the ice sweet tea, and does the sugar dissolve? No, it's like it just kind of stays there. I stir it. Maybe it settles to the bottom. Maybe the tiniest bit of it dissolves. But no, it's just like it's not dissolved. It is like horrible. So I'm like, okay, I messed up making it sweet tea. Like adding the ice was the nail in the coffin to this drink. I might as well go get boba at this point. How should I make sweet tea correctly? I should brew it and then add sugar right after when it's still hot. And then when I add all the sugar when it's still hot, I add a bunch of sugar there. Then maybe I can cool it down afterwards. I can ice it, cool it down, and there'll be a lot of sugar dissolved. Huh? Yeah, it's tea with a bunch of sugar. Sweet tea. Black tea with a bunch of, yeah, basically. And there's variations, but yeah. Huh? Sorry? We're doing advisory, but we're going to finish this page first. Sorry.
This isn't recorded.
Whatever. Y'all got extra moments on your test. So for example, lemonade. Lemonade is also something you want to serve iced, but has a lot of sugar in it. So really, you should be adding this sugar when you're preparing that lemonade when it's still warm, and then you ice it after you dissolve all the sugar. Okay, so let's learn these three vocab terms really quick. Saturated, unsaturated, and supersaturated. So a saturated solution is when you dissolve the max. So I added a bunch of sugar to like my sweet tea and no more is going to dissolve. It starts settling at the bottom. Like I try and mix it and it just settles at the bottom and nothing mixes. So how can you tell if a solution is saturated? When it settles. When solute settles at the bottom. Let's say when solute settles. Or like you cannot dissolve any more solute. It just, I mean, you see at the bottom, I think that's the clearest indicator of your thing. What is an unsaturated solution? Well, it just means you have not reached a maximum. So not max solute dissolved. You're allowed to dissolve more. So how can you tell if a solution is unsaturated? Well, first of all, you're not going to see anything settled at the bottom. But if you add like a pinch of like sugar or a pinch of salt or like whatever you're trying to dissolve and you mix it, it should still dissolve. So you can say add a little solute and it still dissolves. There's nothing that settles at the bottom. So that would be an unsaturated solution. Finally, we have something called a supersaturated solution. So this kind of goes back to the example of sweet tea. Like maybe I cannot dissolve too much more when it's ice cold, but maybe when I made it warmer and I dissolved a bunch of sugar then when it was warmer, I saturated it, and then I made it colder again, it's still the same level of sweetness. So we can say it somehow reaches supersaturated state. It's beyond the maximum amount that could be dissolved, beyond the maximum amount of sugar that can be dissolved. So let's say supersaturated is beyond the max solute limit dissolved. So how does the solution become supersaturated? Normally you can like use temperature changes. So for example, I could saturate it at a higher temperature and then cool it down to a lower temperature and then now it's supersaturated. Like that's the normal way to get a supersaturated solution. And how can you tell if a solution is supersaturated? Well, other than like knowing you made it supersaturated, you can trigger the solute to come out of the solution. So if you're able to do that, if you're able to make solute come out of the solution, then it was probably supersaturated. You can do this in two ways. Normally, like you can like agitate it a bit with something like a little bit more solute, maybe like scratching it with some glass, adding some sort of crystal in there, and all of a sudden, all this solute will just settle at the bottom of your container magically. I mean, it doesn't happen that often. Another way, like the solute just comes out of solution, is just wait. Sometimes you just wait over time. Like let's say I have this really sweet tea, and it's like really ice cold, but there's no ice in it, so it's not being watered down. Now, if I keep it ice cold and I just keep it there in the fridge with no ice in it, then over time that sugar will just kind of like start settling out of solution on its own. So that's how you can tell if something's super saturated. If like over time things just start settling out of the solution, you start getting things appearing at the bottom of your container. All right, questions from this lesson, y'all? All right, we'll learn more stuff next class period, but this is where we're going to stop for now.